and we did our mass balance primarily, and we had the student example of people coming in versus people who are staying in versus people who goes out. So that's conservation of mass. Conservation of momentum, we said Newton's second law, after the sum of forces equals to ma. So I write it in a derivative form because I have mass times acceleration. Acceleration is simply the derivative of velocity over time. So I can expand it in an integral-like form. The sum of forces, I have various forces that I have to account for. Now, primarily, there's main forces that we need to focus on, which is, we said body forces. If we're working with gases, then it's negligible, so I don't have to worry about that. And if I don't have an electrical magnetic system, I can ignore all the body forces. I have pressure forces, viscous forces, and external forces. Viscous forces will assume our systems are inviscid and account for the viscous forces through efficiencies of components, so in the engine in general. So I have two main forces, pressure forces and external forces. External forces, most likely a propulsion system is attached to some vehicle of some sort, an aircraft, boat, or whatever it is that you want to classify as a vehicle. And we have an external force that is driven by drag primarily, and that is an opposing force and the pressure force within the full engine in terms of overall surface integration. So using that, we did the derivation, we got a general form for it. Now if I'm assuming steady state, this term goes out. If I'm assuming one-dimensional, we did an example on it right here. And this is primarily the main equation that we need to start using. And we've used the propulsion system where we have some inlet and some exit with some fuel flow here. We did our conservation of mass, which is like a mixer again. And conservation of momentum, we outline the mass flux multiplied by, or mass flow multiplied by the velocities, and the pressure forces and the external forces, and we outline this equation in that example. So pretty straightforward in terms of application. I'm just rehashing them again. Now, conservation of energy, which is the first law of thermo. We said total energy is a composition of internal energy, kinetic energy, and potential energy. So for a closed system, the total energy is equal to the rate of change of heat plus work. Now, if I am looking at the rate of change, which is the total unsteady system, then I have Q dot at 1 W dot, and from there, getting the substantial derivative of that is equal to the summation of work. Then we apply Reynolds transfer theorem to it, where we have a control volume and tracking what goes in versus what goes out, same process as we've been doing so far. And I outline my sum of work and sum of heat and sum of work. And we'll do a few examples on those. Now we said work. If we think of a propulsion system, there is three types of works that I have to deal with. I have to deal with shaft work, I have to deal with boundary work, and body work. Now, since body work is negligible at this stage, so we'll say, well, neglect the body work. We'll focus on shaft work and boundary work. Shaft work is primarily if I have a gas-driven engine. So think of hypothetically now of an engine. If I have a turbine or I have a compressor, I'm going to have a shaft that's producing work, and that's that work. Now, I have a gas that I'm flowing through my engine, and that gas is actually going to produce my boundary work. So I'm trying to tailor my first law of thermo to a propulsion system in advance. And I'm going to do an example on it, but for now, these are the two critical works that I have to deal with. Now, shaft work is easy because it's a mechanical rotary work that I can account for easily. Now, boundary work is a bit challenging because, well, this is fluid that I'm carrying in my hand right now. It's deformable, it's invisible, and I need to account for how it expands or contracts in my engine. Through a compressor, I'm actually compressing that gas, and through a turbine, I'm expanding that gas and extracting work. So to account for that boundary work, I had to sort of simulate a pseudo formation of it. And we said, well, it's easy to visualize it in a piston form. If I have a piston and I have my gas, I heat it up, it expands, and that's what I call as a boundary work. Now, that's a piston where it's a closed loop system. My propulsion system is an open loop system where I have gas coming into my propulsion system, so how do I handle that? Well, that gas is the same thing like the piston itself. It's like a slug flow that passes through and compresses whatever volume I have. And this is where we said, if I have flow coming into my engine, I'm going to simulate it as a rectangular box of some sort, enters my control volume, and changes my characteristics of my control volume. So by doing that, I'm taking the same formulation that I have right here and applying it here. Now my work is equal to pressure times volume, same principle as a piston. And pressure is multiplied by volume is simply mass over density. Now density is your specific volume. 1 over density is your specific volume. And so this is mass. Now if I'm looking at the rate of change of that over time, so d work over time is equal to P specific volume mass dt. Well, the rate of change of mass over time, I could just name it as m dot. So all I did was simplify my equation of my boundary work. So I don't have to account for boundary work as a dynamic quantity all the time. I could account for it through simply P specific volume m dot. And I could do it for the outlet. So this is what comes in versus what goes out right here, what left my control volume. So from there, I took that information and I knew my definition of enthalpy, which is enthalpy is equal to internal energy plus the pressure times volume. So by doing that, my general form of my energy equation was in terms of internal energy, if you remember here, for example, right here. Total energy is in form of internal energy, kinetic energy, and potential energy. So if I take this and substitute it here, what do I got? I get rho multiplied by internal energy, kinetic energy, and potential energy. But I just said I'm going to decompose work and expand it into two terms, primarily the boundary work and shaft work. So by doing that, I could get rid of this with this and substitute it with enthalpy. And it's easier to track enthalpy than to track internal energy and the PV work, the flow work. PV represents your flow work, or your gas or medium that you're dealing with. So it simply becomes rho, enthalpy, kinetic energy, and potential energy. Now, the normal component, so velocity multiplied by the normal component by ds. What does that represent? Or where did that come from? Mass flow. Why? Because density is there. Very good. Mass flow. So this represents your m dot. And so, well, I have it. Okay, I have it here. All right. So anyway, so Q, W dot, the summation of mass flow multiplied by these quantities that is coming in versus what goes out is equal to 0. And that's my general form that I need to worry about in applying it to my propulsion system. I'm just showing you derivation so you know where these equations come from. They're not just coming from magic. It's the same principles that you understand. Now, why is this important? Because once you graduate and work for a propulsion company, you might have to tailor some of these equations to the principles that you're dealing with. If you're working on advanced technology that requires an additional component that you don't have in this equation, you have to account for it. But you understand it. That's the important thing. It's understanding it. But this is the equation that you only need throughout this whole course, because I'm not going to have you add a weird component in there unless you're working on something advanced. So, but it's the same stuff. It's heat, work, mass times enthalpy, kinetic energy, potential energy. That's it. Okay? Straightforward? Make sense? We're going to be doing examples on it. Anyway, so this is the first law of thermal. I kind of have it on there, but we have to keep in mind that this form is steady state and it's one dimension. Okay? Given this is the equation I have to deal with the first law, it doesn't really restrict the path of how I move forward or backwards throughout the system. I could generate heat from work and work from heat with no restrictions whatsoever. And this is where the second law would actually apply. And we started to say, well, if I have a hot system applying to an engine, and we're saying everything goes to work, that's not physically possible because I end up having heat loss. Think of your car engine like we mentioned. So meaning that the first law is definitely applicable to all systems. However, there's restrictions of certain paths that I have to account for. And there's a reversible path, irreversible, and practically an impossible path that I have to account for. So in this case, we've got heat being applied to the heat engine, and I got work. And we said, well, this is not possible because that would mean 100% efficiency of all my heat is going towards work. And from experience, it's impossible to get that. You're going to get a certain type of efficiency, however, you're going to always get heat loss, which we outlined right here, right here. So we had heat in, and we said, well, I'm going to get work output, but I'm always going to get heat loss, undesired heat loss that I can't control. So most of your careers are going to be spent on trying to reduce this as much as you can. Because it's not what you're trying to get at. You're trying to get as much work as possible, as much thrust as possible out of the engine, but you're trying to minimize this. Any efficiency losses that you're having through your system. So that's one. The other one we said, well, I could go from hot to cold. That's easy. But I can't go from cold to hot without doing any kind of work. And one of your colleagues mentioned that, oh, we need to add work in order to go from cold to hot. Think of your AC system. We are using electricity to drive from a system to extract heat from your car or your room to a hot outdoor environment. So that's where the AC system will come into play. So that's another irreversible process you have to account for as part of the restriction to the first law. Now also I have to deal with friction as an irreversible process. If I have any temperature gradients of some sort, which is right here, I'm always going to have heat loss. No matter how much you insulate this, it's not going to be a perfect insulation. You're always going to have that heat transfer because you're going to have a hot and a cold medium next to each other. And as a result of that, you're always going to get one directional heat transfer from hot to cold. It's the nature of physics, so we have to deal with it, but we have to account for it. So these are some of the reversibilities, and another one is non-equilibrium. We said, well, this is assuming perfect flow going through my engine. So this is a piston where we said, well, how non-equilibrium would really work. It's essentially saying that if I am compressing this piston right here, the pressure is uniform. Well, that's not the real scenario that happens. When your engine, your piston engine is actually compressing that gas, you've got a frontal area that's high pressure, and where the cylinder head is actually a low pressure. So until the piston goes up and things become more uniform, but you've got this non-uniformity that is going on. Now this is a piston engine. How does this relate to my gas turbine engine or propulsion-based system? Well, same thing as blades. I've got flow that is coming at it for compressors, turbines, and whatnot. If I get any separation or non-uniformity in pressure, that induces a non-equilibrium process for me, which is translated to my overall efficiency, and we're going to account for it shortly. So as a result of that, we outlined the consequences of the conservation laws, the things that I just talked about. So you already have in your notes. I'm not going to get into the details of that, but I wanted to move on and introduce entropy, which we're familiar with, but let's do conservation of entropy because it is the key component that is going to define our efficiency losses of our components. And we're going to do examples on it. We're good on time, so I want to do a few examples. All right, so primarily using the second law. So all this was an introductory to entropy.